This is mainly about the birth and death of the stars and the universe itself. We start at the origin of the universe, which is the Big Bang theory. I think you should be all familiar with it. This is the most commonly accepted theory. It is first proposed in the late 1920s. It states that there was an infinitely small, infinitely dense point which contained everything in the universe, which is also called singularity. It is incredibly dense and hot, as you can predict it. The Big Bang is believed to have occurred between 10 and 15 billion years ago. And two elements, hydrogen and helium, were created, along with small amounts of lithium and barium, with a prediction inside the model. So after the creation of the Big Bang theory, people start to find the evidence of the Big Bang. In 1929, Edwin Hubble studied the light given out by the galaxies, and he noticed that light from most galaxies was shifted to the red end. So he proposed Hubble's law afterwards. You can see the right diagram. It is the shift of the spectrum of some galaxies. It all shifts to the right, which is the red end. This shows the electromagnetic radiation of these galaxies become longer in wavelengths as they become further away from us. Hubble finds the rate at which the galaxy is moving is directly proportional to the distance from us, which gives us a very nice law. The H naught in the law is called Hubble's constant, which is constant, and this d is the proper distance of the galaxy from us. In other words, the universe is expanding, because if an object is further away, moves further, and the rate is proportional to the distance, it is equivalent as the whole space is expanding at the same rate. After Hubble's law finds the evidence of the expansion of our universe, two other physicists calculated independently in 1946 and 1948 predict that our universe we should be able to detect microwave radiation from everywhere in our universe based on the Big Bang theory. It is later called cosmic microwave background radiation. This can be detected using spectral antenna, and it is described as echoes of the Big Bang explosion. In 1965, two physicists in the Bayer laboratories accidentally discovered this microwave radiation. At that point, they do not know and thought it is the background noise of the radio telescope. But after they released this result, the Decades group, which is the guy on the right, found that it is actually the cosmic microwave radiation. And the two physicists here got the Nobel Prize because of it. In fact, the snow that one can see on tube TV is also due part of the microwave background radiation. By theory, the original temperature of radiation should be 3000 Kelvin, and today is only 3 Kelvin. So with the calculation, we can see that the light travels 13.7 billion years, which is commonly accepted as the age of the universe, although there are many other theories predict otherwise. In June 2001, a probe called Wilkinson microwave and an anisotropy probe captured the glow of the Big Bang by detecting the temperature changes. This is a diagram produced by this probe. We can see, although they have different colors, the temperature is almost homogeneous throughout the whole universe, because from the coolest to the hottest, the difference is plus minus 200 microkelvin. However, there are small fluctuations as the diagram shows. But this diagram proves that the Big Bang must have taken place at the same time everywhere, which is also an evidence of the Big Bang theory. So we can see we have three evidence of the Big Bang. First is expansion of the universe proved by the Hubble's law. Second one is abundance of the light elements, hydrogen, helium, and lithium. We can see the abundance of hydrogen is much larger than any other elements, and the abundance of hydrogen plus helium takes most part of the elements inside our universe. So it is the same as what predicted by the Big Bang theory. And only hydrogen and helium and a very small amount of other elements can be predicted inside the Big Bang itself. The third evidence is the cosmic microwave background radiation, as we talked about above. However, the Big Bang theory also has some limitations. First one is structure of the universe. As the Big Bang theory states that the universe starts have the singularity. It is basically have no description of the structure of the universe. So we cannot predict what the universe is like from the Big Bang theory. The second one is the fluctuations on the background radiation. It is because if the singularity is homogeneous, there's no evidence to see why there's fluctuations. And how do they rotate stars and galaxies? The famous physicist Alan Guth proposed a theory to solve these problems afterward. The theory is called inflation. It is announced around the time of 1971 or 1980. And the theory states that the early universe experienced the exponential expansion of space and the supercooling process, which only takes place around 10 to the power of minus 33 to 10 to the power of minus 32 seconds, which is very, very small. But the rate is extremely high as the space is expanded by the factor of at least 10 to the power of 78, which is usually larger than any number you can see, but smaller than the number of particles inside the universe. This is a diagram shows the general history of the universe. You can see the very, very left side it's an inflation right after the Big Bang. However, the inflation is have a very significant effect because it produces two waves as seen, which is gravitational waves and density waves. These two waves cause the fluctuation and the spread of energy inside the universe, which makes our universe almost flat, but still have some fluctuations which produce the concentration of matters which can produce the galaxies afterwards. So after all the particles become the atoms and elements, and they form normal matters we can see, after around 380,000 years, the neutral hydrogen forms, as we can see from the diagram. So this gives a precondition to form galaxies and stars. So now we are going to talk about the stellar evolution. Let's start from the origin of the stars, which is commonly known as the interstellar medium. The interstellar medium is defined as the matter that exists in the space between the star system and the galaxy. The matter can include gases in ionic, atomic, and molecular form, as well as dust and cosmic rays. It is usually made up of around 90% of hydrogen and around 10% of helium. Very small amounts are other things. So the regions of this medium are denser than normal and are known as nebula, as they are cloud-like appearance. So it is in this interstellar cloud that stars are formed. This is a photo of the giant molecular cloud, and you can see the violent burst of an infant star. A giant molecular cloud is where a star usually born from. It is one kind of interstellar medium, which is formed by molecular form of gas, which is usually hydrogen H2. And the stars are commonly formed inside this kind of interstellar medium. So how does it form? Usually a shock wave from a supernova can hit one of these clouds, and this triggers a gravitational collapse, which puts the gas and dust particles together. As the cloud condenses, smaller regions break off into something called globules. And these globules eventually form hot gaseous spheres known as protostars. A protostar is not a true star in the sense that it has not started nuclear fusion. And when gas and dust continue to accrete on the protostars, the temperature rises. When the core reaches 10 million Kelvin, nuclear fusion begins. This one is the artistic diagram of the protostar. You can see the matters around it get attracted by the star and condense on it. So when temperature rises to the point, a star is born and nuclear fusion begins. The nuclear fusion provides the outward pressure and the inward gravity. This force creates equilibrium, and you can see from the inward arrows and outward arrows on the diagram, and allows the star to sustain a definite size and shape. Otherwise, if the two forces cannot have equilibrium, the star will either be very, very large that the temperature drops to stop the nuclear fusion, or they will be condensed together, as we can see in the part of the death of the star. The star is now in a state called hydrostatic equilibrium. So before we continue to talk about the journey of the stars, let's talk about one diagram to classify the stars, which is called HR diagram. This shows the temperature against the luminosity with stars. From this kind of diagram, we can see the characteristics of stars easily. This is one example of the HR diagram. From left to right is higher temperature to lower temperature. From up to down is higher luminosity to lower luminosity. You can see there's one kind. There's one group of the stars from the upper left to lower right. It's called main sequence. And around 90% of all the stars are in the main sequence. This diagram shows some famous stars in our galaxy inside the extra diagram. Usually the luminosity against the temperature of the star is dependent on the mass of the stars. So we can see usually upper left are stars with higher mass, and lower right are stars with lower mass. However, you can see the white dwarf. Although they are hot, but they have generally smaller luminosities, and the supergiants, although they have comparably high luminosities but lower temperatures, as the volume of supergiant is higher than the main sequence, and white dwarfs that of white dwarfs are lower than main sequence. Another kind of star is called pre-main sequence star, which is from the journey of the star from the protostar to the main sequence of star. You can see from the diagram that different mass of stars spend different lengths of time on this path. If the star is very massive, it spends shorter time. Like 15 times mass of our sun only spent 60,000 years from a protostar to a main sequence star. However, stars as our sun reaches the main sequence in around 15 million years. There are one kind of stars called brown dwarf, which is a star that cannot sustain hydrogen fusion reaction. So they fail to become a main sequence star. It usually have an upper limit around 25 to 80 Jupiter mass, which is much smaller than the mass of our sun.
Is Jupiter a brown dwarf?
No, Jupiter is not considered a brown dwarf yet. So we're now going to talk about the main sequence. Main sequence is that star has a delicate balance between the force of gravity and force of pressure, as we talked about before. And it has a distinguished characteristics, which is it has the nuclear fusion of hydrogen inside its core, and only hydrogen. It is the longest phase of a star's life. So there's no other kind of fusion in the main sequence star. Now we separate the stars into different masses. The small stars is commonly considered as a mass below 0.8 of solar mass. There is no life beyond the main sequence. Because the low mass stars, by theory, it will live for trillions of years, which is obviously larger than the age of the universe and larger than the predicted lifespan of our universe. So the low mass of stars is predicted to live forever. Even if it will not live forever, currently we do not have any knowledge of it after the main sequence. This is a photo of this kind of small stars, which can also be called a red dwarf, which is different from the brown dwarf. Now we are going to talk about stars that are similar to our sun, which has a mass of around 0.8 to 8 solar masses. And it lived around 10 billion years in the main sequence. After 10 billion years, the medium-sized stars will build up helium inside its core. As we can see from the diagram on the left, the helium is built up mainly inside its core. So the helium in the core does not provide any energy because it do not go through nuclear fusion. And at the point when hydrogen in the core cannot sustain nuclear fusion, there's no energy produced by the star, so it's left main sequence. After which, because there's no pressure from the core will collapse, and the gravitational energy heats up the core. It also heats up the hydrogen shell. So initially the temperature in the shell is not high enough to sustain the fusion, now it is high enough. So the hydrogen in the shell starts to fuse, and the pressure is produced inside the shell. So the gravitational pull is not able to sustain the shell, and the shell gets to expand and expand. So the star gets bigger. It is known as the red giant. This is what the sun will be like when it goes into a red giant. The diameter of it will increase at around 200 times. So afterwards, the core will continue to collapse due to the gravity until the temperature reaches 100 million Kelvin. At this point, helium will start to fuse, and it is fusing to carbon. This signals the last stage of the medium star life, as there is no energy to fuse carbon into heavier elements. And you can see this is the star when the helium is fusing. The carbon ash is right in the center of the star, and then it's a helium core, and then it's hydrogen core. So what happens when the sun runs out helium inside its core? The carbon will not go through any other fusion. The core will shrink and the surface will expand. As the surface will expand larger than the red giant, it is called the red supergiant, and the surface temperature will be even lower. As the surface continues to expand and expand, it will eventually drift away to the outer space and form a nebula called a planetary nebula, a specific kind of nebula produced by the medium-sized star. So what happens inside this core? With no source of energy to stop its gravitational collapse, star will shrink until it reaches a point called electron degeneracy. The star will now known as a white dwarf, and will continue to radiate energy until it remains dead and cool. This diagram shows how the electron degeneracy happens. The pressure from motion of atoms and the gravity makes the core to collapse. So when the electron shells are almost touch each other, the electromagnetic force generates the repulsion force. At this point, the atoms will not become any closer, and it's called electron degeneracy. This is the reason of the formation of the white dwarf. Otherwise, it will collapse, and we will talk about it later. This is a photo of the white dwarf, series A and B. Series B is a white dwarf. You can see it's very small as an arrow. A white dwarf usually have a volume comparable to our Earth, but a mass comparable to the Sun. So it is extremely dense, although it is less dense than the neutron star we are going to talk about later. There's no more fusion, and the white dwarf grow by heat itself. So the temperature of it continue to decrease, and when it eventually cools down, it's called a black dwarf. This is the theoretical limit of the largest maximum mass of the white dwarf star. Its commonly accepted value is 1.39 of the solar mass. If the left core of the star is larger than the limit, a white dwarf will not form. Instead, a neutron star or a black hole will form. And this kind of star is no longer called medium-sized stars. It will be called massive stars. A massive star usually has mass higher than 8 times of solar mass. It follows the same evolutionary track as medium-sized stars up to the point of the carbon core. However, it is very different afterwards. You can see the core of these massive stars have different share of elements. So when the core of these stars eventually reach 600 million Kelvin, the carbon will begin to fuse and produce hydrogen. When it reaches 1 billion Kelvin, carbon will fuse to produce oxygen, neon, and magnesium. Once the core reaches 1 billion Kelvin, oxygen will continue to fuse, which produces silicon. Then at 2 billion Kelvin, the silicon will produce iron. Specifically, iron 56. There is no nuclear fusion afterwards because iron is the heaviest element you can get from nuclear fusion. Afterwards, the element requires more energy to get heavier. So they require to absorb energy instead of release energy. If you need the element to be fused to higher masses. This process is called nucleosynthesis inside the star. And this produces almost all the elements between helium and iron. Iron core do not have outward pressure because it will not go to nuclear fuse. So the gravity will win and stars collapse rapidly. Because the mass of star is larger than the medium-sized star, the core is obviously more massive, and electron degeneracy cannot stop it from the gravitational pull. Atomic structure cannot stop it. So the electroprotons are basically clasped together. So obviously they are going to produce neutrons. The neutrons will push together by the force of gravity. And there are equal number of electrons and protons inside the star. So all the left will be neutrons, as you can see here. Because the repulsion force between neutrons is much larger than the electromagnetic force between electron protons, which is caused by strong nuclear force. So the neutrons will not stay there. They repulse each other and get outside. At this point, it's called a supernova explosion. Within 1 second, the metal is shown back into the interstellar medium, and the metal rush outwards fused with metals rushing inwards. Because the energy of the explosion towards all the elements are artificially made. The deliveries of the supernova can create a nebula. This is a photo of this kind of nebula. So what happens inside the core? Usually, with core largest 1.4 solar mass, a neutron star are made. The neutron stars are spotted by the neutron degeneracy, which is the repulsion force of the neutrons. The neutron stars are so dense that 1 teaspoon of the material from neutron star would weigh around billions of tons. And the stars rotate very quickly. The highest observed value is 716 revolutions per second. If the core is more massive than 2.4 to 3 mass of the Sun, it is not a confirmed value. The neutron degeneracy will not be able to support the star. The star will be too massive to exist as a star anymore, and the black hole will be formed. The black hole has its name because it has a gravitational pull which is so strong that even light cannot escape from it. So it is absolutely black. And the points formed by points at which the light cannot escape are called the event horizon. The radius of event horizon is called as Goldwater radius. It is theoretically calculated from general relativity as follows: 2 times the gravitational constant times mass of the core divided by the square of the speed of light. This is an artistic diagram of the black hole. As usually, the telescope cannot capture a black hole directly. So an artistic diagram will be a better representation, as it's predicted by the theory. When you go closer, what will you see when you go closer to the black hole? This is also how the videos in the movie Interstellar are created. Now we have seen all the evolution track of different mass of the stars. So this is the end of the stellar evolution part. So we are going to talk about the death of the universe. So let's see a video.
One day the universe will die, but why and how? And will the universe be dead forever? And how do we know that?
Talk about 3 different
First of
kinds
all,
of
the universe is expanding, and not only that, the rate of its expansion is accelerating. The reason? Dark energy. Dark energy is a strange phenomenon that scientists believe permeates the universe. Until 1998, we thought that the universe must work a bit like a ball that you throw into the sky. The ball moves up, but at some point it has to come down again. But the expansion of the universe is actually speeding up. That's like throwing the ball up and watching it fly away faster and faster and faster. Where is this acceleration coming from? Well, we don't know, but we call it dark energy. Einstein thought of it first and then decided it was stupid. Now, astrophysicists have decided it is plausible. Trouble is, this is all very theoretical, and we don't actually know what the properties of dark energy are. But there are various theories, and they lead us to 3 scenarios for the end of the universe. 1. The Big Rip. Since its birth, the universe has been expanding. For unknown reasons, new space is created everywhere equally. The space between galaxies expands, so they move apart. The space inside galaxies also expands, but here gravity is strong enough to keep them together. In the Big Rip scenario, the expansion accelerates up to a point where space expands so fast that gravity can't compensate for this effect anymore. The result is a big rip. At first, only large structures like galaxies are torn apart, since space between the single objects expands very fast. Next, big bodies like black holes, stars, and planets die. Their gravity isn't strong enough to keep them together, so they dissolve into their components. In the end, space would expand faster than the speed of light. Atoms would now be affected, and they would just disband. Once space is expanding faster than light, no particle in the universe can interact with any other particle anymore. The universe would dissolve into countless lonely particles that won't be able to touch anything else in a strange, timeless universe. And you thought you felt lonely. 2. Heat death, or a big freeze. In a nutshell, the difference between the Big Rip and heat death is that in a heat death scenario, matter stays intact and is converted over an incredibly long but finite period of time into radiation while the universe expands forever. But how does this work? Let's talk about entropy. Every system tends towards the state of highest entropy, like when we have a latte macchiato. Initially, it has different regions, but over time they will cool down and disintegrate until it's uniform. And this also applies to the universe. So while the universe gets bigger and bigger, matter slowly decays and spreads out. At some point, after lots of generations of stars, all the gas clouds necessary to form stars will be exhausted, so the universe will turn dark. The remaining suns will die. Black holes will slowly degenerate and evaporate over trillions of years due to what's known as Hawking radiation. When this process is complete, only a dilute gas of photons and light particles remains until even this decays. All activity in the universe ceases at this point. Entropy is at its maximum, and the universe is dead forever. Unless, theoretically, it might be possible that after an incredibly long amount of time, there might be a spontaneous entropy decrease as a result of something called quantum tunneling, leading to a new Big Bang. 3. Big Crunch and Big Bounce. This is the most uplifting scenario. If there is less dark energy than we think, or it decreases over time, gravity will be the dominating force in the universe one day. In a few trillion years, the rate of expansion of the universe will slow down and stop. After that, it reverses. Galaxies will race at each other, merging as the universe becomes smaller and smaller. Since a smaller universe also means a hotter universe, temperatures rise everywhere all at once. 100,000 years before the Big Crunch, background radiation would be hotter than the surfaces of most stars, which means that they would be cooked from the outside. Minutes before the Big Crunch happens, atom cores are ripped apart before supermassive black holes devour everything. Finally, all black holes would merge into a supermassive mega black hole that contains the entire mass of the universe, and in the last moment before the Big Crunch, it would devour the universe, including itself. The Big Bounce theory states that this has happened a lot of times, and that the universe goes through an infinite cycle of expansion and contraction. Well, wouldn't that be nice? So what will actually happen to the universe in the end? At the moment, heat death seems the most likely, but we at Kurzgesagt hope that this dead forever stuff is wrong, and the universe will start over and over again. We don't know for sure either way, so let's just assume the most uplifting theory is true.
This is the end of my presentation.